Next, you make a shot. You have like 60 points.
All right, hi everybody.
Hello. Next, you have to score 30 for the shot.
How are you guys doing? Okay. So today we're gonna talk about the inverse trig functions. So we've been talking about sine, cosine, tangent, secant, cosecant, cotangent for a while. At the very beginning, we talked briefly about the inverse trig functions just in order to, like when we're solving a right triangle, to find the angle measures. We're going to look a little bit more in depth about what these inverse trig functions can do and can't do. And then look a little bit more at how we can, how to use them effectively, okay? So, if we look at this top picture, that top picture is just a graph of sine x, right? Right? We're familiar with that. We just got done graphing sine and cosine functions. That's just the graph of regular old plain parent function y equals sine x. Now, if you guys remember back from Algebra 2 last year, you guys talked about inverse functions. One way to find the graph of an inverse function is to take your function and reflect it across the line y equals x. So that's what I've done in this picture here. Here's the line y equals x. Here's the graph of y equals x. So that guy is the inverse of y equals sine x. Is everybody okay with that? Look at that graph of y equals sine x. There's a problem there. Does anybody see what the problem is?
They cross. They cross in the middle.
What do you mean they cross in the middle? What are they?
I gotta know that somewhere.
You think on it a little bit. If it clarifies, butt in and let me know. Alex, you were saying something too?
Is it like the y sin x and the opposite of it? They're like crossing each other?
No, they should. So if they both intersect the line y equals x, they should, they'll intersect then there because they're just reflections of each other across that line. So that's not the problem, but there's a problem with that graph of y equals sine inverse. Think back to the very beginning of Algebra 1. If you saw a graph that looked like that, what could you say about it? I'm sorry, of Algebra 2. You guys were talking about this at the start of Algebra 2. You look at this graph right here. You should be able to say something about that graph. Nick.
Y sin x.
Yeah, that's the graph I'm talking about. What would you say about it, though?
Just like the power. What here is that just
That's just the notation we write for the inverse. So it doesn't mean like 1 over sine x. That means something different. So that's just part of the name we give. We got to give it a name. That's the way we're going to name it. Okay? So if I look at that graph of y equals sine inverse x, is that a function? Is that the graph of a function?
No.
No. Why not, Mark?
They have one of the same points.
So was there a test that we used to check for that? Vertical line test. Does the graph of y equals sine inverse pass a vertical line test? No, right? Because there's like some vertical line I can draw that intersects the graph in more than one location, right? So, because it's not a function, I can't build a program into a calculator to output the values for it, because it's not well defined. For any input, how many outputs am I going to have? Infinitely many, which is a problem for a calculator, right? So what are we going to do here? Well, what we did in Algebra 2 when we ran into a situation like this is we restricted the domain of the function. So what we say is, okay, well, what if I only take sine x from negative pi over 2 to positive pi over 2? What if I take just that part of y equals sine x? Now that covers all the possible y coordinates that y equals sine x can have, right? It covers all the y's between negative 1 and positive 1. And now if I do the inverse of that, I'm going to get the blue graph. Is that blue graph a function? Yes. Why?
It passes the vertical line.
Passes a vertical line test. So that's what we're going to do. Okay? So that's what we have here. This is the graph of y equals sine inverse of x. Everybody okay? So this is just giving you an idea of like what's going to be the problem here in a minute when we get to how do we use this function. Okay? So remember for y equals sine x, the domain was all real numbers, right? Oops. But we just restricted that down to here. The range was negative 1 to 1, but we restricted that, when we restricted the domain, we did it in such a way that the range was not also restricted, right? So if this is my function and its domain and range, what can I say about the domain and range of its inverse? Do you guys remember the rule for this from Algebra 2? Well, they're not exactly reciprocal. Not negatives turn to positives. So remember when you found an inverse algebraically, the procedure was you get the x by itself and then you switch the x and y's, right? What happens to domains and ranges if I switch the x and y?
They switch.
They switch, right? The domain for my function becomes the range for the inverse. The range for our function becomes the domain for our inverse. Is everybody okay there? For cosine, we have to do a similar restriction. I'm not going to bother drawing all the graphs this time to show it to you. I'm just going to state that we do it. So the domain for cosine inverse, still negative 1 to 1, but its range is going to be 0 to pi because I have a different I have to put a different restriction on cosine than I did on sine to make sure that the inverse is a function still. Alex?
How do you get 0 and pi for the domain for the?
So I had to do a similar restriction for cosine, but because cosine starts and ends at a different spot.
So you just like find like the domain from the left or the right side, and then you just like switch the
So like the graph of cosine is basically the same, except the y-axis is here. So I just went from there to there, right? Which is 0 to pi. Does that make sense? So I did the same exact thing. When I restricted the values, I had to do different values to cover negative 1 to 1. So that's all. And then if I have tangent, so the same thing, we'll do a domain restriction. But tangent was weird, right? Remember, tangent had those vertical asymptotes to it, so the range for tangent is still going to be all real numbers. Which means the domain for tangent inverse will also be all real numbers, but the domain will be only from negative pi over 2 to positive pi over 2. Now notice that we have a parenthesis on tangent where we had brackets everywhere else, right? What's the difference between the parenthesis and bracket again? Perfect. Yeah, so the parenthesis means that endpoint, the negative pi over 2, is not included, where the bracket doesn't mean it is included. Why does tangent have a parenthesis there instead of a bracket? Remember what the graph of tangent looks like? What feature does the graph of tangent have that the graph of sine and cosine does not? Yeah, it has those vertical asymptotes, right? Guess where those happen at? So if I make my inverse then, those vertical asymptotes become horizontal asymptotes because the x's and y's switch. So again, this is like negative pi over 2 and positive pi over 2. So those aren't in the set of possible outputs because we know the graph can't cross an asymptote, right? Does that feel okay? This set of information, if I was making a note card for chapter 4, would be information that I think would be pretty good to put on my note card. In this first section of 4.1, we're going to look at several different skills that I want you guys to be able to demonstrate later on when it comes to quiz or test time. We're only going to do one skill today. Okay? One of the several skills today. The skill that I want to work on today is using the unit circle to evaluate sine, cosine, tangent inverses. Everybody good with that plan? So we're just going to do a bunch of examples of kind of different ways I can ask this question. What's up? Yeah, you should have your own copy of a unit circle. I gave everybody one. There's lots of seats that are a lot closer to the board than the one you've chosen too. Just saying, can only make it so big. Happy to make it a little bigger, but there's only so much I can do there. So, if you still have your own copy of the unit circle, you should take it out to follow along with right now. If you don't still have your own copy of the unit circle, I have extras on top of the file cabinet. You should have this out when you're doing the homework. You can't, in fact, you can't do the homework without this. Okay? Got to have it. Hey, Brady.
What up?
All right. So the first thing that I want to do is I want to look at the problem. It says find the exact value of sine inverse -1/2 without a calculator. So in your trigonometry class, if the problem asks for exact value and without a calculator, almost definitely the tool that you need to use is the unit circle. Because the unit circle is basically just a paper calculator, right? It's an exact value calculator. It's basically all it is. So the first thing I'm going to do is I'm going to observe that we're looking at sine inverse. The range for sine inverse is -π/2 to +π/2. So I'm going to go and look at my unit circle and try to figure out what quadrants are covered by -π/2 to +π/2. So since my angles, I have one that's negative and one for positive, I'm going to have to do this in 2 steps. So I'm going to start at 0, and then I'm going to go to -π/2. Which way do I go on my unit circle if I'm going to do a negative angle? Clockwise or counterclockwise?
Clockwise.
Clockwise. So how much is a quadrant again? How many degrees is that? 90 degrees, which is the same as how many radians? π/2. So that's covering quadrant 4. Everybody okay there? Okay. Now I'm going to figure out what's covering, or what quadrant is covered by π/2. So I do the same thing. I start at 0, and I rotate counterclockwise this time because it's positive, ending at π/2. And I covered quadrant 1. Is everybody okay with that? So, the answer that I'm looking for has to lie in either quadrant 4 or quadrant 1. Everybody good with how I figured that out? Okay. Now, I remember on the unit circle, sine theta is, how do I find sine on the unit circle? It's the y coordinate. So I'm going to go and look for where the y coordinate is -1/2. So I'm going to just look at the y coordinates. So +1, +√3/2, root 2 over 2, positive a half, 0, negative 1/2, negative root 2 over 2, negative root 3 over 2, negative 1. That's the only place right there. Everybody agree? That corresponds to the angle 11 pi over 6. Nick.
Do you just go from pi over 2 all the way down to negative pi? Or
Well,
negative?
I just looked in quadrants 1 and 4 because that's where I knew my answer was. So I only looked there. I noticed that, yes, if you keep looking, negative 1/2 is a y coordinate elsewhere, but I don't care about that one because it's not where my answer is going to live. Has to live in there. Is that good? Perfect. Good observation, though. Everybody so far so good? Okay, we're almost done, but we have a little problem. What is that little problem? We're so close, but it's not quite there. Is 11 pi over 6 between negative pi over 2 and positive pi over 2? Yeah, it's not, is it? Right, 11 over 6 is like 1.86 or something. That's bigger than like negative 1/2 to positive, right? What do? We don't have the right answer, but are we like, well, what's wrong? We didn't do anything wrong. Everything we did was good. What we need is an angle that's between negative pi over 2 and positive pi over 2 and is in the same spot as 11 pi over 6. What do we call angles like that? Coterminal angles, exactly. Let's just find an angle coterminal to 11 pi over 6 that does lie in between negative pi over 2 and positive pi over 2. Now I feel like we're going to get there. How do we find coterminal angles? Add or subtract 360 degrees, but we're working in radians. What's 360 in radians? 2 pi. So I'm going to either add or subtract 2 pi from 11 pi over 6. Now, should I be adding or subtracting? Subtracting. Excellent. Why? Because this guy was too big, right? It was past positive 1/2. I need it to be smaller. I better subtract. If I'm going to subtract 2 pi from 11 pi over 6, what do I need to have? Common denominator. What would that common denominator be? 6 is right. So that's going to be 11 pi over 6 minus 12 pi over 6. What's 11 pi over 6 minus 12 pi over 6? Negative 1 pi over 6, or let's just write negative pi over 6. That's our answer. That feel okay?
How'd you get like the negative pi over 2 and pi over 2 out of that? Like to begin with.
So we got this answer, right?
Or like the blue and green.
Oh, this is the range for sine inverse.
So that's just like always there.
Always there. At least for this type of problem. We'll show you another type of problem where like we'll look for an answer in a different spot. Okay.
So will there be a problem where we won't have the difficult?
Yeah, so your final step is to check to see if your answer lies inside of the range. If it does, stop. You're done. If it doesn't, then we have to find something coterminal to that answer that does lie in the range we're looking for. Feel good? Keep on going. Let's do another example of this, right? That's okay. Next problem we're going to look at is the cosine inverse of negative root 3 over 2. So first thing I'm going to do, cosine inverse, I know the range is from 0 to pi. Is okay there? So I'm going to see what quadrants are covered by the angles from 0 to pi. Well, this one, I don't have a negative and positive, right? So I can do this just in one sweep. So if I start at 0 and I go to pi, those are all going to be positive angles, right? Which way do I go if I'm going positive angles? Clockwise or counterclockwise? Counterclockwise. So I start at 0. I just passed pi over 2. I'm going to keep going. And I ended at pi. Right, feel good with what I did there? So what quadrants did I cover? 1 and 2. So, on the unit circle, cosine is how do I find cosine in the unit circle? The x coordinate. Yeah. So I'm going to say then that I'm looking for where x is equal to negative root 3 over 2. Where am I looking for that x coordinate? Quadrant 1 or 2, exactly. So I'm just going to look. I have positive 1. Nope. Positive, positive, positive. None of those. Everybody's good? And I have negative 1/2. Ooh, that's getting closer. Negative root 2 over 2. Negative root 3 over 2. Found it. And then negative 1. That's the only spot it happens. Just once. That corresponds to the angle 5 pi over 6. The fraction 5 over 6, is that bigger than 1 or less than 1? Less than 1, right? In fact, it's between 0 and 1, isn't it? So guess what? Nick, do we need to do anything to adjust this guy? No, it's good. No coterminal needed because 5 pi over 6 lands in our range. No adjustment needed. That's not bad. How do you guys feel so far? It's okay? Okay? We're going to keep going, do another example of this, and then I'm going to put a little tweak to it. Still kind of the same process, but we're going to add one more layer onto it. Everybody's okay? All right. Do one more example like this. So here we have tangent inverse is equal to tangent inverse of negative 1. So we start same way. We look at what type of trig function we're dealing with. What's the range on tangent inverse? I go back and I look at that box of green stuff I circled. Negative root 2 over 2 to positive root 2 over 2. Now, notice here, this interval has a negative end and a positive end, so I'm going to have to do that with two different sweeps when I look for my quadrant. So if I look at my first sweep, oh dear, just erase. Why did you erase? That's negative, so I'm going to start at 0. Which way do I go for negative? Clockwise. How far is pi over 2 in degrees? 90. How much is that? 1 quadrant. So I'm going clockwise, 1 quadrant. What did I cover? Quadrant 4. And then for positive root 2 over, or pi over 2, again, we start at 0. This time it's positive, so we're going counterclockwise. So that's quadrant 1. Ready? So far, so good. So on the unit circle, how do we find tangent? Y coordinate over X coordinate. So here we're going to say then Y over X has to equal 1. Remember, let's make that positive 1. Where is that 1 coming from? The problem, I changed it from negative 1 to positive 1 right now because I want something different to happen. Is everybody okay? I made that little adjustment. Everybody's mad? So the littlest erasure I will have to make, right? But like, what X and Y am I going to look for now? If Y over X has to equal 1, what coordinates should I be looking for? That's confusing, right? Well, what if I just multiply this? What if I multiply both sides by X? Right? Let's get rid of the fraction. That'll separate the X and Y coordinates. What's that going to leave me with? Y is equal to X. Oh! So I'm just looking for the spot where X and Y are equal. Okay. Fair enough. So 0 and 1 not equal. 1/2 and then root 3 over 2 not equal. Root 2 over 2, root 2 over 2. Aha! Those are equal. Everybody agree? Mm-hmm. How many times is this going to happen? Just once, right? So I don't need to keep looking. So the answer there should be pi over 4 is pi over 4 in between pi over 2 and negative pi over 2? Or sorry, negative pi over 2 and positive pi over 2? Yes, right? We have negative 0.5 to positive 0.5. 0.25 is in between those, right? I'm just converting my fractions into decimals. Sometimes it's easier to tell if something's in between if everything is a decimal, right? You can just kind of forget about the pi's. So that's it, and we're done. How do you guys feel? Have you figured out when you're going to have that coterminal adjustment? When is that going to happen?
When your answers like not like between your two.
Visually, where is that answer going to be?
So 2 quadrants as well.
Inside quadrant 4. On problems like this, if your answer is in quadrant 4, that's the only time you're gonna have to do the coterminal adjustment. If your answer's in quadrants 1 or 2, no problem. Quadrant 4 requires the coterminal.
You're not being quadrant three.
Is that 45?
For this type of problem, it cannot be. We're gonna look at another example, or we're gonna put a little tweak to this problem where we can start getting answers anywhere. Ready, so far so good? Alright. Are we ready for the next version of this problem? Yeah? Alright. So the presentation of this looks pretty similar, right? It says solve for sine theta equal to 1/2, where theta is between pi/2 and 3pi/2. So the first thing I'm going to do is I'm going to get the theta by itself. What do I have to do to both sides of this equation to cancel out the sine? Well, we do sine inverse to both sides, right? Right, so saying sine theta is equal to 1/2 is equivalent to just saying theta is sine inverse of 1/2. Everybody's okay there? Okay. Now, I'm going to use this piece. Here I notice that sine theta is greater than 0. Right? 1/2 is a positive value. And I'm going to go back to all silly turtles crawl to determine what quadrants sine is positive. Well, remember the capital letters tell you what trig functions are positive in that quadrant, right? A for all. So sine is positive in quadrant 1. S for sine, so sine is positive in quadrant 2 also. Everybody's okay there? Now, I'm going to use this piece and figure out what quadrants are covered by pi/2 to 3pi/2. Okay, so far so good. Remember, each quadrant is 1/2. So I'm going to start at 0. These are positive values, so which way am I going to count? Counterclockwise. So 0, 1/2, 1, 1.5. So I start here, and I go to here. So we're covering quadrants 2 and 3. So where is my answer for this? Have to lie. Which quadrant does it have to be in? 2. Because it's the only quadrant that satisfies the yellow part that I highlighted and the green part that I highlighted. Everybody feel good? Okay?
Why is the green part highlighted? Like, okay, maybe it's, oh, okay, got it.
From this, right?
Okay, I see.
So in Q2, what are we going to look for? Where the y coordinate is equal to 1/2. Come on. There we go. So there's my spot. Five pi over 6. Jacob. Sure. Okay. So very similar problem, right? Feels very similar. There's a little bit different build, but we're still going to go to the unit circle the same way. Look for the coordinate and look for the angle. But figuring out where to look on the unit circle is going to be a different task, right? A little bit different feel to doing that for these type of problems. Everybody okay? Let's do that again a couple more times. Make sure we got it. Sound good? Okay. You like this though? Is this okay? It's pretty visual. If you're a visual person, this is usually goes okay. Now let's wait and do that last. And then I want we're looking for cosine theta equal negative 1/2 between 3 pi and 4 pi. So again, cosine theta is negative. Where is cosine negative?
The sign.
S and T, right? Because in A, all cosine is positive, and in C, cosine is positive. So I'm looking at quadrants 2 and 3. Everybody feel good how I got that? Just using my all silly turtles crawl. Remember we learned that before and I warned you we're going to need it again. This is us needing it again. Yes?
Oh, why are you putting in S? Shouldn't it be in C?
Well, cosine, C means cosine is positive there.
Oh.
The letter means that's where it's positive. So this time we're looking for a negative. So I need the ones that aren't C. Does that make sense?
Mm-hmm.
Okay. All right. Then we go and we look at the interval we're given. So we'll just count around. So which way are we going to be counting? Clockwise or counterclockwise? Oh, no. Counterclockwise because the angles are positive angles, right? You probably would have gone the right direction. You just forgot the difference between clockwise and counterclockwise. We're counting by each quadrant is a half a pi, right? So we're 0, half, 1, 1.5, 2, 2.5, 3. That's my start. 3.5, 4. So we cover quadrants 3 and 4. Is everybody okay there? And if you're more comfortable doing decimals, write decimals. You don't have to write the fractions, as long as you know, like, you convert the fraction, all your fractions to decimals on this and just go all decimal when you're drawing this stuff. That's totally fine. No big deal. You'll get the right answers. Okay? Now the final answer you should report as a fraction. But like if your steps in between, if you want to write decimals, then write decimals. No big deal. So far so good? Okay. So, what am I going to do now? On the unit circle, where am I looking? Okay, in quadrant 3. What are we looking for? X equals -1/2. Why am I looking for an x coordinate, not a y? Cosine. Right? So far, so good, everybody? So if I look in quadrant 3, that's what I want. So my answer is 4 pi over 3, right? Mark, you're dead on. You beat me to the punch. He said that's not quite right because my answer needs to be between 3 pi and 4 pi. 4 over 3 is like 1.3 as a decimal. Oh no! Did we do something wrong? Yeah, we just need to find a coterminal answer to this. Is our answer too big or too small?
Too small.
Too small. Should we add in 2 pi then or subtracting? Adding. To add 4 pi over 3 and 2 pi, what do I need to have? Common denominator. What would the common denominator be in this case? 3. What's 4 pi over 3 plus 6 pi over 3? 10 pi over 3. As a decimal, 10 over 3 is 3.3. That's between 3 and 4. I'm satisfied that I have the correct answer at this point. How do you guys feel so far? Do one more example, and then I'm going to hand out a worksheet and let you guys work on that the remainder of the period. Sound good? It's going okay though? Feels doable? Answer. Yeah, go ahead. All right. One more example. So here we're going to do tan theta is equal to root 3 over 3 from -5 pi to -4 pi. This will be like the hardest variation of this kind of problem I think I can cook up. So we start by noticing that tan theta is positive. So when I all silly turtles crawl this, where are we living?
3 or 1.
3 and 1. Are you happy with how we did that? Remember, A for all of them positive, T for tangent positive. The next thing we're going to do is figure out what quadrants are covered by -5 pi to -4 pi. Since those angles are negative, which direction am I going? Clockwise. And how am I counting? By halves, right? So -1/2, -1, -1.5, -2, -2.5, -3, -3.5, -4, that's my start, -4.5, -5, that's my end. Is everybody okay with how I counted around to find the quadrants? Again, can you do this without drawing a picture? I don't think so. I think it'd be rough, right? Like the picture helps so much on figuring out where to be looking for. Okay, I draw the picture every time I do one of these. I need it. Could I do it in my head if I thought hard enough? Maybe, but it's like too much stuff to carry.
Yeah.
You know, like writing it down, the picture makes it really easy to remember what's where. Okay, so where am I looking then? In what quadrant? In quadrant 3. And what are we looking for? Because it's tangent, I'm looking for y over x equals root 3 over 3. Ew, boy. What am I going to do with this, guys? Who likes fractions? I don't, right? Nope. So let's multiply something by both sides of this to get rid of the fraction. What are the two denominators? X and 3. Let's multiply both sides by 3x, right? Everybody's okay with that? And then let's pick either to get the x or y by itself. Sound good? Since we don't have that. My suggestion here would be to divide by the radical. Is the one that I'd want to do. In general, that's be the easiest. So let's do that to get the x by itself. Now, how do I reduce 3 divided by root 3? Oh, you mean top and bottom? You want to rationalize that? Yeah, okay, we can do that. We can do it that way. So I have 3 root 3 over 3, right? And then I'm looking for. I'm looking for the spot on the unit circle where the x-coordinate is square root 3 times the y-coordinate. So what does the x-coordinate gotta have in it? A square root 3. I mean, that shouldn't have been too much of a stretch, right? Because it's square root 3 times something. So that's what we're gonna do, look. That's where we're gonna look. Everybody ready? Let's pop that in there. So we're looking in quadrant 3, and we're looking for the spot where the x-coordinate has a square root 3 in it. If I take the y-coordinate, negative 1/2, and I multiply it by the square root of 3, do I get the x-coordinate? Yeah, I do, right? Everybody's okay? This is the worst one. The tangents are always the hardest ones to figure out, especially when it's not just one. So my answer there should be 7 pi over 6. Is that in the range that it needs to be? No, our range was from negative 4 pi to negative 5, or negative 5 pi to negative 4 pi, right? Is 7 pi over 6 too big or too small? Too big. Too big, so we should subtract 2 pi. I'm gonna write 2 pi with a common denominator already, just to expedite this process a little bit since we're on the last one. I think by now we've gotten the picture with the common denominator thing. Is that okay with everybody? Yeah. All right. So I get negative 5 pi over 6. Is that between negative 5 pi and negative 4 pi? No, it's not, is it? Oh, Mom. What do I have to do then?
You have to minus it by 4 pi.
I have to minus it again. And negative 17 pi over 6, that's like negative 2.8. Still not there. What do I do? Minus it again. Oh my gosh. Oh my goodness, what happened here? Did I do some subtraction wrong? Because now that's 2. Oh no, that's, I'm sorry, that's fine. So that's negative 4.8, and that is in between negative 4 and negative 5. Whew. Okay. Ah! Okay, and we're done.